Let's solve this problem. They have given that RAM access time equal to 10 nanoseconds, hard disk access time equal to 1000 nanoseconds, and also they are saying that they are using two level paging, which means they are using multi-level paging with two levels of page tables. We will have process one level of page table and another level of page table, right? We will start from here and then we will go into the byte. That is what we have been seeing so far, right? Fine. Also, they have given that page hit rate equal to 0.9. We can also say this as page hit percentage equal to 90%, right? They both are same, right? 90 divided by 100 is 0.9. Fine. Now let's calculate the average memory access time. See, you can follow any method. You can either follow first method or second method. Anyway, we will solve both in this video. Let me solve the first method. Average memory access time equal to 90% of the times what we are going to do, let us assume our byte is present inside the RAM. In that case, what we will do, we will have three levels of accesses, right? Which means we will go into the RAM, we will go into the page table, first outer level page table, fine. After accessing the outer level page table, we will go into the inner level page table, fine. Now after going into the inner level page table, we will get the frame number and then we will go into the process and then we will get the process, right? In case if the byte in the process is present inside the RAM. In case if the byte in the process is present inside the RAM, I will access two levels of page table and then I will go into the process and then get the byte, right? So effectively it is taking three memory accesses, right? Since we have two levels of paging, we need three memory accesses, and so I can say that 3 into 10 nanoseconds, which is 30 nanoseconds, right? Fine. In case if the byte is present inside the RAM. Now in case if the byte is not present inside the RAM, then what will happen? We will definitely access all these things, right? Because we will go into the first level page table, outer level page table, and then we will go into the inner level page table, and then we will go into the RAM, and then we will go into the hard disk, and then we will move the data from hard disk to RAM. After that, we will read the data from the RAM, right? Effectively, there are three memory accesses and one hard disk access, right? See, we have two levels of paging, so it will take two memory accesses. After accessing two levels of page tables, we will understand that our byte is not present inside the RAM. So we will go into the hard disk and then we will move the data to RAM. For that, it will take one hard disk access, right? Two levels of paging will take two memory access. One hard disk access will take one hard disk access, and then after moving the data to RAM, I will read the data from RAM. For that, it will take one RAM access. So effectively, I am going to have three RAM access, which is 3 into 10, which is 30 nanoseconds. Also, I am going to have one hard disk access, 1000 nanoseconds, right? So in case if I simplify this, what will happen? So I am going to cancel both the zeros, 0, 0, 0, 0, right? So 9 into 3 is 27 nanoseconds. Fine. Now what will happen here? It is 1030, right? See, I can erase this and I can write this as 1030 nanoseconds, right? Let me erase it. It is 1030 nanoseconds. Fine. I'm going to cancel both these zeros, right? Both these zeros for both these zeros. Fine. It is 103 nanoseconds. 103 nanoseconds. So effectively we are getting 130 nanoseconds. What does it mean? In case if I wanted to access a byte in our computer, on average it is going to take 130 nanoseconds, right? See, one thing you can understand is always our average will fall between both these values, right? RAM and hard disk. It is very clear, right? It is just like average marks of a student in a classroom will fall between the highest mark scorer and lowest mark scorer, right? It will fall between both. That is what I am going to say this. So now let's solve using the second method. See, coming to second method, one thing is for sure, we are going to have three memory accesses, right? Because initially we will access both the page tables, fine. We will access both the page tables, so it is 100% of the times I am going to access both the page tables. For that it will take 20 nanoseconds. Fine. After accessing the page table, I'm going to definitely read the data from the RAM, right? Which means either in case if the data is present inside the RAM, I will directly read from the RAM. In case if the data is not present in the RAM, I will read the data from RAM after moving it from hard disk to RAM, right? So effectively, definitely I'm going to read the data from the RAM 100% of the times. 100% of the times I'm going to read the data from the RAM. See, this is for page table, right? This is for page table. This is for reading the data from RAM. Data from RAM. Fine. So 100% of the times we are going to have both these things. Fine. Now when will we have access the hard disk? Only in case of page fault, right? In case if the byte is not present inside the RAM. Which means if page hit rate equal to 90%, then page miss rate is 10%, right? Only during 10% of the times we are going to additionally access the hard disk. Otherwise, we are going to only access the RAM. Only in case of page fault, we are going to have some additional access time, and that is nothing but 10%, and that will happen only during 10% of the times. And how much time is it? It is 1000 nanoseconds, right? It is 1000 nanoseconds. Now, in case if you simplify this, you will get the same answer. Let's see this. So, 100% of the times it is 20 nanoseconds plus 100% of the times it is 10 nanoseconds. I can simply cancel them out. So, 20 plus 10 is 30. 30 nanoseconds, fine. Plus both the zeros I can cancel it out, right? 10 into 10 is 100, right? So, it is 100 nanoseconds. So 30 nanoseconds plus 100 nanoseconds is 130 nanoseconds. So effectively we are getting the same answer because both these formulas mean one and the same. Fine.